All right, good morning. Today we are going to be going over graphing exponential functions. This is the beginning of Unit 8, and it's a different kind of function where we're going to be dealing with exponential growth and exponential decay, where things are either growing really fast once the x values turn positive, or they start slowing down a lot, and we'll see what those graphs look like. So I'm going to graph three different versions of, in this case, this would be an exponential growth function, but we're going to plug in x values to show what the function would do. So with exponential functions, you're going to have a base value. In this case, it would be 2 raised to an exponent. So we're going to be plugging in these values for x in the exponent, and then graphing them to show what they're going to be doing. So if I do 2 to the negative 1, we talked about last unit that meant that you pick up all of this when you raise it to a negative and you put it in the denominator. And so this would be 1/2. When you raise anything to the 0 power, you get 1. 2 to the first is 2. 2 squared would be 4. So if we come over here and graph that, if I go to negative 1, I'm at 1/2. Which would be about right there. And then if I go to 0, 1, that would be my y-intercept, and that's going to be a really important point that we'll talk about in a little while. And then we have 2, 4, or I'm sorry, 1, 2, and then 2, 4. And then even if I plug in 3, 2 to the third is 2 times 2 times 2, which would be 8. And now I'm all the way up here. So if you notice, we start off pretty flat, and we grow exponentially and start going up really fast. And so the left side of this graph actually is always going to be, and that's not very good, always going to be above the x-axis. Okay, there's going to be an invisible, and we could plug in numbers to talk about it, but there's an invisible line right here, and that's going to be called an asymptote, which we'll talk about in a little while. But so then if we go to 3 cubed and I plug in the same numbers, negative 1, 0, 1, and 2, this would become 1/3, still not 0, but 1. Does anything raised to the 0 is 1. And then we have 3 to the first is 3. And then 3 squared would be 9. So if I graph those values, we're going to have negative 1 comma 1/3, 0, 1 in the same spot, and then I go to 1, 3 and 2, 9. And so our graph is going to be super flat and then start curving up. And then since that base value, the 3 compared to the 2 that we had a second ago, since that base value is bigger, I'm growing even faster. So then if we do it one more time, we could do negative 1, 0, 1, and 2. This would be 1/4, 1, 4, and 16. So if you notice again, the values are going to start be growing crazy fast after we hit our y-intercept. So we're going to be right there. We're going to be flat again. We're going to hit the green. We're still going to hit 0, 1. But then we're going to go to 1, 4 and 2, 16, which is like way up here. So if I draw that, all of a sudden, and that's not a good drawing. Hold on. If I draw that accurately, I'm way up there. Grow really fast. So this is exponential growth, and then we would be increasing everywhere. As I go left to right, we'd be increasing everywhere. The domain for all of these is negative infinity to infinity, but the range, which is really important, is going to be 0, infinity. And again, that's because of this orange asymptote at x equals 0. And so asymptotes are special lines that you will never, ever cross. And so in this case, for exponential growth, you will never, ever get a y value that is negative. We're never going to be below the x-axis. Okay, and that's because, like we talked about, when I plug in -1, it pushes it to the denominator. It doesn't make the value negative, just pushes it to the bottom and makes it a fraction. That's less than 1. Okay, so if we go to number 2, there's a big contrast in the type of number that we have for our base, and for these, we have base values that are now less than 1. So for the first ones, we had base values that were greater than 1. And so that's when we had the exponential growth. So these were growth. And then for these down here, since the base value is less than 1, but also greater than 0, it's going to be exponential decay. And our numbers are going to support that. So again, if I plug in -1, 0, 1, and 2, -1 raised to, or I'm sorry, 1/2 raised to the negative first is +2, because it's going to push everything. It's going to flip your fraction. It makes it a 2. So that's 1/2 raised to the negative first. Well, you flip your fraction, these numbers switch spots, which makes the 2. Anything raised to the 0 power is 1. And then 1/2 raised to the first is 1/2. And then 1/2 squared, so 1/2 times 1/2 would be 1/4. And so if you notice, now as I am plugging in x values, my y values are actually going to get smaller. So when I go to graph this, -1, 2, 0, 1, 1 and 1/2, 2 and 1/4, my numbers are going to start getting smaller. But let's get an idea of what's going on as we go to the left. So if I plug in -2, that would be 1/2 -2. So that negative again flips the fraction. So now it's 2 over 1, but now being squared, so that would be 4. So -2, 4, and then we could keep going, and it would be -3 to 9. And so our graph is decreasing really fast, hits my y-intercept, and then is going to flatten out and once again not ever get a y value that is negative. And we could plug in numbers all day long to see if that is true. So for 1/3 raised to the x power, -1, 0, 1, and 2, you're going to get 3, 1, 1/3, and 1/9, which is going to look like -1, 3, 0, 1, 1/3, 1/9 is teeny tiny, very close to that x-axis. But again, it's going to look something like this. Okay, and then even the last one with the 1/4, the different base value, same numbers, but the behavior is acting the same. It's just becoming more dramatic in how it's moving. It's becoming more dramatic. So -1, 4, 0, 1, and then I almost can't even graph those because they're so small. But we're decreasing really fast, and we hit that y-intercept, and then we're going to flatten out and not cross that x-axis. Okay, so this would be the exponential decay because I'm starting up high and then we're going down. Our numbers are getting smaller. Our result, our y value, is getting smaller. So these are decreasing, and the domain would still be all x values, -infinity to infinity, and the range would still be the lowest point of 0, but I don't actually ever hit 0 to infinity. Okay, so these exponential graphs, one's going up, one's going down, but their domain and range is the same because we're hitting all of the x values and we're not getting any y values that are less than 0. Okay, so there's your exponential growth and decay. So if we go to the next page, kind of what we were just talking about is being supported by this. So we have a b value base right here. And when b is greater than 1, that's when you're going to be getting that growth and you're going to get this pattern right here. Okay, Same thing, like we were talking about with the second one, we have exponential decay. When that b value is between 0 and 1, really, really important that it's between 0 and 1, you get that decreasing pattern exponential decay. Okay. The reason we can't have a b value that is less than 0 is because if I do -4 to the x, it's going to do something with that negative. That negative is going to cause a specific transformation that we'll talk about in just a second. Okay. So all exponential parent functions have -infinity to infinity for the domain. The range is always going to be 0 to infinity, which means it's always going to be, the graph is always going to be above the x-axis for the parent function. There is a horizontal asymptote at y equals 0. And then there's a really, really important point. And I'm actually going to change this key point, and we're going to say that it's called the turning point. And I mentioned it a second ago, and it's that y-intercept at 0, 1. It may not always be the y-intercept, but for those graphs that we talked about, it's that point right there that is a really, really important point, because that's where I go from probably flat to increasing really fast, or I go from decreasing really fast to then flattening out and slowing down. So that's a really important point. Okay. The other points would be that we can have 1 comma whatever the b value is, or it's -1 comma 1 over the b value. So that could help you when you plug in 1 and -1. You're always increasing when the b value is greater than 1, and you'd be decreasing when b is between 0 and 1. Okay, so those are some important things you need to remember and probably memorize and be able to utilize. Okay, so with transformations with exponential functions, they work the same way as any other function. They're just kind of written in specific spots. Okay, so we still have left and right horizontal translations. We still have up and down translations. And we have, when multiplied by an a value or a leading coefficient out in front, it's going to still stretch it, give you a vertical stretch. Or you could get, and I'm fine with you saying a vertical shrink. Vertical shrink. Okay. Compressed is fine. If you want to say compressed, that's fine. But a vertical shrink is also fine. Okay. And it depends on what that a value that you're multiplying out in front is. Okay. So if we go to number 3, it says to identify each of the following as exponential growth or exponential decay, and then describe the movement from f of x to g of x. So from the very, very beginning, we should be able to look at that b value and determine whether it's growth or decay. Well, that number, the 3, the b value, is bigger than 1, so this has to be an exponential growth equation. Okay, and then as I go from the parent, in this case, to g of x, there are specific transformations that are happening over here that are going to impact our graph. And so when it says to just describe, we're literally just going to put words that describe exactly what's happening. So this +1 is in the very, very back. Just like the other functions, it does whatever it says, and you go up or down. So this would be up 1. Okay. You can imagine, like when we did parabolas, you did f of x, and maybe it was x minus 2 squared, and how we made a big deal about that part being inside the parentheses. Well, you do the opposite, and you go left and right. That idea is the same, except now you're going to find it in the exponent. So this is x minus 2, all in the exponent. So that is going to make the graph move right 2. Okay, and then our a value for this one is actually just 1, but with that negative, the negative out in front is going to cause us to reflect over the x-axis, which is what it did before. Okay, so they're the same transformations, kind of written in a different, just being, maybe not really written different, but being applied to a different, different function. But you do pretty much the same thing. So for this one, automatically the b value, the base value, is less than 1 and greater than 0. So that would mean this is a decay. So it's going to look something like that. And then we have our transformations that are happening to it. So the minus 2 in the back is down 2. Okay. And then this one's a little bit different. On number 3, we had the negative out in front. And so that reflected over the x-axis. If the negative is out in front, x-axis. But now we can actually have negative exponents that we've kind of done some stuff with and how that moves things to the denominator or to the numerator. But for our graphs, when you have a negative in the exponent, it causes you to reflect not over the x-axis, but now we're going to reflect over the y-axis as well. Okay, and if we think about the math for that for a second, if I raise 3/4 to the negative first power, well, the negative power causes the fraction to flip. And so this goes from a b value being less than 1, where it would be decay, and it turns it into a b value that's greater than 1, and so that would turn into a growth. And so we go from, with the negative exponent, we can go from decay to growth, where it would look like this. But if I reflect that over the y-axis, this would be the y-axis right there, then I'm going to be having this arrow on this side, and that arrow up here, and that turns into that growth. Okay, so that's kind of what's happening. So we can have a reflection over the y-axis, but it actually kind of switches it from growth or decay. And so being able to recognize this negative in the exponent is going to be really, really important. Okay, so there's 3 and 4. Now let's go put it all together and we can actually graph them. So number 5, we need to fill out this important information and then go put it all in the graph together. So right away, our b value, our base, is greater than 1, so this has to be a growth. So in your brain, you need to think your graph is starting out looking like that, and then I'm going to apply the transformations to it. If you want, you can probably just go graph the parent with no transformations to get an idea of where you're starting. And so we have that just 2 to the x is going to hit that turning point at 0, 1, and then it's just going to grow. It's going to grow something like that. Okay, but then the transformation that we have is causing this to move up 3. So the curve of my graph is not going to change. The whole graph is just being pushed up 3. So the key point, and again, I'm changing this to say turning point. Yours may already say turning point. But the turning point was 0, 1, and now it's going to move up to 0, 4. Okay, so this is going to be at 0, 4. The horizontal asymptote of the original parent is at y equals 0. But when I push the entire graph up 4, it's not just pushing the turning point, it's pushing literally all of it. And so the horizontal asymptote also is going to get pushed up 4 and is now going to be at y equals 4. So if I was going to put, or I'm saying the wrong number, I'm sorry, we're pushing it up 3. I misspoke, we're pushing it up 3. But I'm going to put, with that turning point right here, it's really important that you go ahead and go draw your new horizontal asymptote because you still can't cross that line. You still cannot cross it. So our graph is going to look something like this. Okay. You know, honestly, I'm probably not drawing this as well as I should. We should probably go ahead and put actual points, especially on the side that it's growing on. So for like the parent, we did on the very first page that if I plug in 1, 2 to the first power is 2, 2 to the second power is 4, 2 to the third power is 8, and so that's what my curve needs to look like. And so let's go ahead and put actual points just to make sure we get it right. So again, for the new one that I just pushed it up, if I go, so you can almost think of this spot right here kind of like your origin. Well, if I go over 1, 2 to the first, you go up 2. 2 to the second, you go up 4. So we're going to be right there. And if I go over 3, 2 to the third would be 8. So that's going to be actually just barely off the graph right there at 11. And then there's your curve. Okay. I do want you to be as precise and as accurate as possible. So that's why I went back and fixed those. So the domain, always negative infinity to infinity, and that's for either one of those equations. And then the range is where you'd have to be careful. If I'm pushing the entire thing up 3, well, then the range cannot go below 3, which means it's 3 to infinity. And very important that this is not a bracket. That is a parentheses. You're not actually ever going to hit 3. You're just going to get really, 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 really close to it infinitely. Okay.